Hello, hello. Hello. Give me a sec. Okay. Starting a little bit behind. Good afternoon. Good afternoon, Lear. Good afternoon,
Hey, good
Vicky.
afternoon.
Thank you. Good afternoon. And good afternoon, Vicky. And good afternoon, Mafine and Victoria and Joel. Hold on. And I know there's no board yet. Hang here with me for a second. Uh, and good afternoon for the double, Vicky. Good afternoon, Raina. Good afternoon, Joel for the double. Good afternoon, Mafine for the double. Good afternoon, Zoe. Good afternoon. Sorry. Sonam. I'm all confused. Good afternoon, Victoria for the double. Good afternoon, Caitlin with the double exclamation point and the thingy emoji thingy. Good afternoon, Roger. Hello, Anthony with the double. With we now have a picture, which is awesome. Thank you. That's totally you should submit for points. All those points are being recorded, even though you guys haven't seen them in a while, and I'm aware of that. Again, may a couple, and again, many of you have gotten back your exam. Many of you have not. I'm aware. I'm just, again, they're just coming and they're coming, and I apologize. I'm just going to keep saying that just so it's clear. Some of you have gotten them, some of you have not. They're just all through all the sections, they're just dribbling in. But hold on, give me a second. We're going to start in a second. Just the board didn't come yet. Hold on. We're just going to get back to, oh, what just happened? Come on. Hold on, hold on. And hello. Oh, yes, I said, what is happening? What? Um, and hello, yes, hello. Okay, bear with me for a second. The board is the board. It's like freezing. The board is frozen. Bear with me, bear with me. Oh, hello. Oh, and hello, Aminata and Reina. Oh, thank you. That's very kind, direct chat person. Okay. Um, okay, I think the board is wait, the board is almost, hold on. Yes.
Good afternoon, Professor.
Good afternoon. Thank you. Good afternoon. I appreciate that. I'm just catching up. The board is not, I'm catching up to the board. Hold on a second. Okay. 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 All right. We're just going to get back to it again. So we're just all in that stage where we're just all just doing what we can to catch up. I'm behind. Some of you are not behind. Some of you are. Um, we're just catching up. There's no new more homeworks. You still can work on this. What I'm everything I'm saying now is based on or helpful to related to the very last homework, Gauss's law. I'm going to start saying things. I'm going to soon start saying things that go from Gauss's law on into our final topic, there's no homework on it of what I'm going to say, such as this. So in other words, the first equation on the board here is what you need to do that entire homework number 7, which I certainly will still accept from people, to put it mildly. The second equation is what I want to get to today. Oh, so funny. Okay. Not funny, but well, fascinating. Okay, what I someone just asked something in the direct chat, which is like it couldn't have been a more perfect question. So what I'm about to say is I'm going to do a little bit more that is directly helpful or relevant to homework 7. I will still definitely take homework 7. Um, I'm going to do a little bit more. The exact little more that I'm going to do right now is exactly what someone just asked about in the direct chat. Um, like the cylinder stuff. That's what I'm going to do right now. Interesting. We're on the same page. Um, but I'm going to use that to then sort of move forward. So I'm not going to go over every single bit of homework 7. I'm giving the central ideas of homework 7 and then and then just use them to catch up with whatever and to understand the final material of the course. And people tend to ask at this point, like, am I still accepting homeworks late or something like that? Well, yes, especially because how could I not? I mean, I still owe you guys stuff. So it's humanity and understanding in both directions. My advice, what I don't want is on the very last day of classes, don't give me a huge pile of like all the homework from the whole semester. That would be a mistake on your part. It would be a mistake. But I will take old homeworks and I will give a lot of credit for them. Not all the credit, but I will give credit for them. But I'll give less and less credit the older they are. So my best advice to anybody who's trying to play catch up as I am, um, my best advice, both for the sake of efficiency, triage for whatever points you're looking to get in the course, and also so that you can optimize your situation on the final exam or whatever's. If you're trying to catch up, or if you old things, go backwards, go from most recent to toward least recent. And also that just helps you understand what's going on in class better. You follow what I'm saying? Okay, that's my and please know that anything you did submit and haven't gotten back, or any game participation points, which I have fallen completely behind in tracking, they're all there. They are all going into your average, like they're in the Google Classroom, right? It's just, even if you haven't gotten stuff back in a while, they're there. Your efforts were not wasted. So they will all be tallied up and included in the end. And same thing, if there's like a homework from a long time ago that you never got feedback on or anything like that, believe me, I know that fact as well. So, I mean, if you know what to do to get a higher score, do it if you want. But if you never found out what to do to get a higher score and I never marked it I will recognize that when I finally go to mark it. And believe me, you'll get generous marking, if that makes sense. Um, uh, okay, something just, all right. So, sorry. Wait, there's something in the chat. Wow. Awesome person in direct chat. So the person in direct chat, I'm not going to name names and I'm going to move on in a second, but this is great. That person knows who that person is. That person may want to spread their thought. Well, I'm going to read the thoughts out loud, not the name, but because this is really true. So first of all, the person says, "Hello, Professor, at some point, can I please go over the cylinder section of homework 7?" Yes, that's exactly what I'm going to do. All right, I was working for 2 hours last night. I'm not entirely sure about it. Fair enough. But then the person says, a lot of the concepts connect if you can wrap your mind around certain things. So I don't think it's so bad if you jump around a little bit. That person's totally right. Like physics, that's always true of physics, but it becomes more and more true, like especially with this topic. Like it's an abstract topic at first, but once you see the hook of it, lots of things wrap around that hook for sure. Hopefully you'll see today and that's, yes. And if you're seeing that, that's a real testament and test for any of you. You'll know that physics is really starting to click for you. Well, when it starts to feel like it's clicking, but specifically when you start seeing various seemingly different questions, when they start actually seeming redundant, or when you're like, wait, all right, I guess this is technically a different question, but I sort of feel like I already kind of did this. Yeah, that's like the nature of physics, is that we're really trying to find the smallest amount of information and the fewest number of concepts to describe the greatest range of phenomena. That is, so if you're seeing that at all, even if you don't totally get it or know what's going on, and again, I'll do it in a minute, but like whenever you go like this in physics, like, Oh, is that all they're saying? Chances are the answer is yes, that's all they're saying. And then chances are that's like a big concept that when in doubt, when the next time you go like, I have no idea what to do here, probably it's use the concept that you initially went, wait, is that all they're saying? Because again, and I will move on, but I cannot emphasize enough that the power of physics is the simplicity. It never looks that way to the outside world, but the power of the physics is the simplicity. What we discover in physics often, or the big fundamental truths in physics, are not truths that you didn't know or that you didn't think were true. It's just truths that you didn't know were so powerful. And that Gauss's law is a prime example of that. So I'm going to go, yeah, yeah. Okay, so I'm seeing in the direct chat, like similarities within diagrams between case one and case two. Absolutely, yes. So I'm going to show you what that person means, what I mean by that when I turn to an example from homework 7 right now. But one second, I just have to respond. Bear with me for a second. But that's what we're going to do. Well, okay, hold on to show you to get this rolling. Okay. So okay, so bear with me for a second. Let me just do this one. Sorry. Okay, where are we? Okay. All right. So what I'm going to So again, I'm talking about concepts that are totally, everything I'm saying is would help you in homework 7, but I'm not being clear about it. Um, I'm just talking. So everything in homework 7, right? They're all, as is the case with classical electrodynamics in general, you're given some distribution, some continuous distribution of charge over here, and you're being asked, what is the field over here? I.e., what is field as a function of displacement from that distribution of charge? So in homework 7, they're walking through different types of shapes that the charge might be configured in, right? So first, like, we did like a dot, then we did like a sphere, um, and we asked, like, what's the field outside the sphere? What's the field inside the sphere? For the insulating sphere, we got two very different answers. Very quickly, by the way, in terms of homework 7, the conducting sphere, I talked a lot about conductors last time. I didn't like literally give you answers. I guess I can give you answers right now. With the conducting sphere, if you're outside and this is sort of what the direct chat person was saying, if you're outside the conducting sphere, the field you're going to get is exactly the same as if you were outside the insulating sphere, which is exactly the same as the field you would get if you were outside a dot, a point source, right? The field you would get is 1 over 4 pi epsilon naught q over r squared, r hat vector, right? It's the same as Coulomb's law. In other words, whether you're outside a conductor or you're outside a sphere, you don't care. You don't know the difference because what you have is a bunch of charge that is arranged symmetrically and creates the same set of field lines outside that sphere. The field lines all radiate out. If you're inside, it makes a difference. If you're inside the conductor, you get the answer we got last week, which is a field that's directly proportional to displacement from the center. That's very surprising. I mean, that's we had to do the calculation to get that result. We certainly didn't know that going in. However, if you're inside a conductor, just to give you an answer that we didn't, if you're inside the conductor, the field is everywhere 0. If it's a stable conductor, if it's a conductor that's been sitting around for a while, the field is everywhere 0 because of the nature of conductors. Now, so that's like 4 different cases of circular kind of things, of spherical kinds of things. What that meant is that last week, what we were doing was cases of 0-dimensional asymmetry. Like, in other words, the commonality between the reason, as a person's pointing out in direct chat, the reason we got the same sort of field function a number of times, the reason that we got a field function that was the same, whether we were outside one sphere or outside a different sphere or outside a dot, is that all of those cases had no asymmetry at all. There was no axis on which something different was happening from all the other axes. That's what I mean when I say 0-dimensional asymmetry. I'm saying that, and what I really mean concretely, like I'm saying dots, a dot is 0-dimensional, right? Like a line is 1-dimensional, a plane is 2-dimensional, a solid is 3-dimensional. A point is 0-dimensional. A sphere is a solid. I'm not saying that a sphere is 0-dimensional, but I am saying that a sphere is like a dot in that they both have 0-dimensional asymmetry. Neither a sphere nor a dot picks out any one axis and treats it as special. Specifically, concretely, what I'm saying is the field lines, the electrostatic field lines from a dot do the same thing that they do from a sphere, which is that they radiate the same way out in all directions. Hold on. Right. So, very good question. So a new question in direct chat. I, th I think I like the way it's being phrased, and I think I want to, well, so I'm going to say Well, I'm gonna raise that question. Good question in the track chat. What I'm definitely saying, I'll answer in a moment. What I'm definitely saying is that all of those spherical type examples, they all have field lines that are radial from a point, and they all have what I would call zero-dimensional asymmetry. Now, but there's more examples in homework 7, right? Like the next set of examples that come in homework 7 are first lines and then cylinders. What I want to say about, and then come plates after that, right? Now, we may or may not get to the plate today, or we may or may not, or ever. We may or may not get to the plate today, but I but with the lines and the cylinder, what we're about to get to right now, what I want to say is the lines and the cylinder have one-dimensional asymmetry. What makes a cylinder similar to a line is that each one of them treats one particular axis of space as special, whether it's a line or a cylinder, right? All of a sudden you have a bunch of, so right here, and I'm not ignoring the question in the chat. I just think it'd be easier for me to answer it. Like once I sort of say this clearly, um, we're about to first look at a line of charge, like a wire, like a bunch of extra protons that are all like jammed together so closely in a line that, that it's a line of charge. To cut to the chase, I think that the field lines from this line of charge, the field lines will look like this. Oops, sorry. The field lines from a line of charge will look like that. But and again, in a minute, this will address the direct chat person, but let's be very careful about my drawing, which is very crude. What I'm drawing right here is a cross section of what's going on. Like I think if you had a line of charge sitting on the table, it would create field lines that would radiate out in all directions. In other words, they'd be like spokes. Like this is a cross section. They would be like legs coming out of a caterpillar going all the way around. And yes, I would call those radial. In other words, I would say that the field lines from a line would have one-dimensional asymmetry. They would radiate out equally in all directions, just like the zero cases, except for one axis. There'd be no field lines along the axis of the charge, right? Like I'm saying, and this is my field line pictures mimic the symmetry or the asymmetry of the thing that causes them. If you have a dot that has no amount of asymmetry at all, the lines will be fully symmetric. If you have a line, a line is symmetric in all directions except one direction. It picks out as special. Like if the line is along the x-axis, now the x-axis is special. So the field lines will pop out in all directions except for x. And yes, to direct chat person, I would call that radial. The only thing I want to, so the person in direct chat says, would it be accurate to say the examples in homework 7 all have radial projections of field lines creating symmetry? What I do want to say is all the examples we did last week, all of the spherical examples, yes. And yes, all the linear or cylindrical examples, yes. I think the last example in homework 7, the plate, I don't think those are radial. So I don't know if that answers your question or not, but this certainly is radial, yes. What I do want to say to everybody is that the field lines are exactly as asymmetric as the thing that causes them. That's how field lines work. If there was nothing causing them, they would just be empty space, which is purely symmetric. The field lines show us that something is happening in space. And it shows us what's happening in space by the extent to which they are asymmetric. So, sorry. Oh, okay. Okay, fair enough. All right. So we're on the same page. Yeah. Okay. And I don't know either at this point, but we're on the same page. Um, uh, so what we're going to look at now, we're going to look at a line of charge. And even though I just sort of covered up a lot of the symbolism with marks, We have a line of charge now, and the way we're going to talk about the line of charge is with density. Just like with that sphere of charge, we said rho was three-dimensional charge density. It was amount of charge per unit volume. Now I've got a line of charge. So we're going to assess it. We're going to identify it by the ratio of charge per unit length. And we're going to call that lambda, right? That's so 1D charge density. But we're asserting for at least this case that the charge density is a constant, lambda naught. Okay, and so the question is, I'll just draw it again over here. So the question is, if this is the line of charge, it's a really long line of charge. The question is, at some point P, what is the E field, magnitude and direction, at a displacement R from that line of charge? That's the question. Um, we've got this line of charge, and we're going to assume so it's uniformly dense with net charge, and we're going to assume that it's really, really long. So we're trying to figure out the field at some displacement from this line, but the displacement R, we're going to assume is much shorter than the length of the whole line. So this diagram is really not drawn very well to scale, actually. We're going to assume that the point P that we're at is really close to the line compared to so that whatever interesting weirdness might be happening at the ends of the line, like we're not concerned with it. So far down there, it doesn't affect us. So the way we do this, right? It's an amount of charge. We're trying to figure out the field near the charge. The whole approach is Gauss's law. I mean, that's the whole topic we're in. That's how you figure out the field from a continuous charge distribution. So we're going to do the procedure that we did last week. The procedure is substep substep A of step 4 of the problem solving method. Substep A, draw the field lines. Always. Well, we've done that. I'll do it again. The field lines look like this. They spoke out of the line of charge. Right? This is across, so if you drew it head on, I mean, if you were looking at it head on, it would look like this. It would be radial. Right? That's the field line. Those are the filling. Then sub-step two, this is the important key part of the whole procedure. Sub-step two, we choose and draw a Gaussian surface at the point that we're interested at. Okay, so we need to choose and draw some kind of closed surface that will enclose a representative sample of the charge, um, and will be at the point, the field point that we're interested in. Um, and remember, any surface, any closed surface at all that we consider will demonstrate Gauss's law. Like Gauss's law will be true of any surface, but where the choice comes in is that we want to choose a surface that is easy to compute. Gauss's law is an integral. The integral is true no matter what, but the integral is computable, is trivial, is simple to integrate if we choose a surface for which E comes out of the integral, right? I We want E as a function of ds to be constant in magnitude and direction, right? So this, oh, okay, there's something in the, yes. Yes, someone's asking the first diagram that I drew, is that how we're supposed to draw the diagram for every question? Yes, please. That is the first diagram that you draw. Sorry, before you even put the field lines in, before the red, like, yeah, like, it's supposed to be the shape of the charge, with the properly labeled total charge and density of charge. So yes, that's what you draw every time. Then in the procedure, we draw the field lines, which I've now done. And then we're supposed to, so good question. Then we're supposed to choose and draw a surface for which the E field is constant in direction and magnitude everywhere at that surface. Okay, that's that's where this whole business of symmetry comes in. What I'm saying is, like, if I, like, in our last problems, we drew spheres. We could draw a sphere again here, and Gauss's law would still be true, but it wouldn't be helpful because the field lines are spoking out of this line. They're not radiating out in all directions. They're radiating out in all directions except the x direction. So we want to draw a shape that captures that one-dimensional asymmetry. In other words, here, well, I'm going to choose a cylinder because a cylinder is a closed shape. I mean, like a tennis ball can with caps on it. A cylinder is a closed shape that has one-dimensional asymmetry. So So here's my diagram now. Like, so here's my line of charge. Um, Here are the field lines. And what I'm going to do is draw a cylinder in my mind. I mean, I'm drawing it on paper, but like there's no actual cylinder in the lab. It's in space in my mind. The lines go on forever. The cylinder does not go on forever. It captures a certain portion of the charge. And but the cylinder is at like the edge of the cylinder, the surface of the cylinder is at point P. Okay, so I'm choosing a cylinder. Now, in broad terms, I chose a cylinder because it mimics the same symmetry as the situation itself. Again, last week we chose spheres. Now I'm choosing cylinder. But now, what does that do for me? Or like, why? What's going on? Well, step three, sub-step three, inspect and verify. The thing I'm verifying is E really constant in direction and magnitude with respect to ds? Well, okay, I'll write that clearly. I mean, what I mean is, and I don't know how you want to write this in your notes, but I'm saying if I now if I now picture myself like as a little mosquito walking around the outside of that cylinder, like taking steps from tile to tile in that cylinder, everywhere I step, and right now, imagine me in the body of the cylinder. I mean, not in the body, in the surface, but along the long roundy surface of the cylinder. Not, in other words, don't worry about the caps for a second. If I'm walking around the outside of that cylinder, stepping one tile at a time, I'm asking myself, whatever tile I step on, am I confident that the angle of the field line is not changing from one tile to the next? And am I confident that the density, the number of the field lines is not changing from one tile to the next? And I'm going to say to you, yes, I am confident. Like, and you'll know I am confident that if I walked around from one tile to another on the outside of like a tennis ball can, no matter where I step on the outside of a tennis ball can, like the radius of that tennis ball can is slamming the tile directly perpendicularly to that tile, right? And whatever number of like whatever number of field lines are coming out over here at this tile is the same as the number that are going over there. Because as one of the direct chat people pointed out before, because all of these lines are radiating out symmetrically in all directions except the x-axis, right? So you'll know that you understand what I'm saying. You'll like you will know that you follow what I'm saying if you see how it would not be true if I drew a cube or I drew a sphere like we did last week. Like last week, we were drawing Gaussian spheres. If I drew a sphere around this situation, the field lines would not flow out of the sphere in a constant manner the way they do here, right? how can I say? Well, certainly the angle. I mean, think about the angle for a minute. Like I'm saying that these field lines are spoking out of this line like legs of a caterpillar. If I drew a sphere around that, each one of the legs would just slam, like each one of these legs is going straight up, right? But if I draw a sphere like that, that means maybe the one right in the center is hitting the top of the sphere at a 90-degree angle, but the one next to it is then not hitting the sphere. Like the one next to it would have to shift, would have to tilt to hit the sphere at a 90-degree angle. Like, right? But they are not shifting. They're all like parallel to each other. At least that cross section is. So you have to picture it in your mind, and you have to stop me if you can't picture it in your mind. But you will know that you're understanding why I chose a cylinder is if you try to picture a sphere and you see that it doesn't work for a sphere or a cube. So I'm going to go on. So I chose a cylinder. So and I'm saying yes, no matter where the field lines hit the surface of this cylinder, they hit in a way that is constant in density and constant in angle. Oh, but one thing, like just to be clear, if you're following this too, um, Gauss's law says that the total flux through a closed surface is fully determined by the charge enclosed by that surface, right? What I'm trying to make sure is that's always true, no matter what. I'm trying to make sure that I've picked a surface for which the integral is like doable. So I'm really trying to ask myself, can I take E out of the integral? That's like the issue here. Well, I'm saying the angle of E is the same everywhere through the length of this cylinder, through the curved part. But you might well ask, well, wait a second though, what's going on the caps of the cylinder? The caps, right? The discs that constitute like the left end and the right end of the Gaussian cylinder, because it is a closed surface. It's like a container, a tennis ball can that has a bottom and a top, so to speak. Well, what about those caps? Well, yeah, you're right. The angle of the field lines through those caps is not 90 degrees. The angle does seem to have changed through the caps. But what the angle is through the caps is literally 0 degrees. And again, if you can picture that, you know we're on the same page. If you are listening to me, but you can't picture in your mind what I'm saying, you really might want to say something in the direct chat because this is all very visual and physical, right? On the caps of the cylinder, the field lines are still like spoking out radially. So they are not perpendicular at all to the caps. Then the degree is no longer 90, but the degree is now 0. I mean, the angle is now 0 degrees. So they're totally flush with the caps. So they're contributing 0 flux to the whole situation. So if an integral is a continuous sum, if technically speaking, in other words, the full flux integral of a full closed surface would be the flux integral plus one of one surface plus one partial surface plus the integral through another partial surface. Like if an integral is a sum, the the results of the integrals through the two caps sum to 0. And so the whole integral is whatever is through the body plus zero plus zero. So any pieces of a surface that have zero flux don't bother us. They don't throw us off. They don't adversely affect the integral. They just contribute nothing to it. So if you're thinking something different is happening in the flux in the end caps, you're correct. But what's happening there is nothing, so it doesn't bother us. By the way, if you're really following what I'm saying, you'll understand that's why we had to specify that this line is really, really long. And we're just cutting off like some segment of it. If we made a cylinder that tried to capture the whole line, or if the line were short enough that we could see what was happening at the ends, funky things could be happening at the ends, and the field lines could be coming out in a funny way. They would be coming out radially in all directions. And then that would make the flux calculation harder. So I am absolutely assuming that this line is very, very long, which is realistic. Again, in the lab, it could just be a meter long, but as long as we're talking, not even. I mean, it could be centimeters long, but as long as we are close enough to the line, like electrons would be, where a centimeter is very, very long compared to where we are, then the ends of the line don't affect us. Okay, so step 4, substep 4. Step 4 is write down the law that I keep referring to that I haven't actually written yet. Write down Gauss's law. So this is the law that we're doing. Um, and that's the law. And then what we do now is all the work, but the math work that it should not be bad at all if we've done the physical drawing work correctly. Some step 5. Uh, okay, so now we're going to do the work of Gauss's law. I just said that, which is hopefully not a lot of work if we've set up our drawing correctly. In other words, I'm just going to recopy. Here's the law. And since we inspected and verified that the E comes out of the integral, that the E is constant in magnitude and direction, we can say this is when I say trivialize the integral, I mean this. I mean take the E out and get rid of the vector symbols, which will always happen, but can only happen, which will always happen if you've chosen your surface correctly. But you need to choose your surface correctly in order to justify this happening. And you might say, well, if I know it's going to happen anyway, well, who cares? What if I choose my surface wrong? I'm still going to say it's happening. But then you'll have the wrong surface area to plug in the next step. So you have to choose your surface correctly to know what surface area to plug in this part. So this is what I mean. So it's E times the full the integral of ds is the full surface area. Always. Now, for a cylinder, the surface area must be like the surface area of cylinder is the area of a cap times the length of the whole cylinder. I should have said right from the start. Sorry that the cylinder. Oh, sorry. Choose a cylinder of where to go? Choose a cylinder radius R and length L. Okay, imagine so the radius of the cylinder definitely has to be R, like the distance from the line of charge to the field point. But let's say that the length of the cylinder is length L. So then the surface area of the cylinder will be 2 pi r. Oh, did I say, sorry, I meant the surface area of a cylinder is 2 pi r L. The circumference of one of the caps times the length of the whole cylinder, right? I mean, notice there's two dimensions of length being invoked here, R and L. That makes sense because it's area we're talking about, two-dimensional, right? The surface area of a cylinder is 2 pi r L. Um, so we have E times 2 pi r L equals charge enclosed over epsilon naught. Now, what is the charge enclosed? Well, the charge enclosed. Now, I didn't enclose all of the charge of the whole thing, right? This is like, here, I'm just going to go to the next page. Like, what charge did I enclose? Well, I didn't enclose all of the charge. I enclosed a certain portion of the charge. I don't know what portion I charged, but I do know, just like last time, the way to know charge enclosed is always to consider density. The density was a constant, so the total density is like, right, I mean, the density of the density of charge that I've invoked is total charge over total length. In other words, this is what I'm trying to say. Right? I mean, if density is charge per length, then the charge that I enclosed is density times length. Oh wait, I'm looking at the if I were to write dA instead of ds. Oh, that's fine. That's totally fine. Someone's asking in the chat, every time I write ds to mean infinitesimal surface, but someone's asking, can they write dA like infinitesimal area? It's totally fine. A lot of books and websites and people use A instead of S. That's totally fine. As long as you know what you're doing and you're consistent, sure, you can use A instead. I tend not to use A because I it gets confused with acceleration in my mind. But yeah, A is fine. Good question. Um, so I have this. So the L's cancel. Oh, okay, that's fine. That's fine. Oh, wow. Someone else is saying in the chat, a different person is saying that they like DA better because they had already sort of known or remembered that like certain areas, like from geometry, like area is 2 pi RL, like I'm doing here. So it was like easier for them to internalize and link to their geometry formulas if they do. That's fine. That's smart. Good. I'm glad you guys are like personal about it. If you want to use A, and that person in particular, the second, so two people are talking about this. That's great. By the way, you should do multiplayer co-op. Well, actually, you don't know the names of the people, whatever. You still can do it. What's interesting, I mean, obviously, this is just like a sidebar, but anything you guys want to talk about is good to me. Like one person was asking, could they do A instead of S? And I'm saying yes, sure. And then another person is actually using capital A because they think of capital A as area, like from geometry formulas. And that makes total sense to me. Sure, if it works. Oh, yeah. Great. Yeah. Yeah. So they're saying that like lowercase a they use for acceleration and capital A for area. Totally fine. Look, to be super honest, that's actually what I used to do. I don't mean used to like in a condescend, even in class as a teacher, I used to do that. I think the reason I stopped, well, because there's other topics that this gets into in vector calculus and other things where it becomes more and more common to stick with the there's no good reason to do what I'm doing. I mean, it's because I'm thinking about other things also that are sort of later, but you know, that's great. If it works for you, do what you're doing, honestly. And I This is so stupid. No, what you're saying is not stupid. Somehow, sometimes when my variable of integration is a capital letter, that makes me queasy sometimes. I don't know. Like, for whatever reason, my professors didn't used to do that, use capital letters for variables of integration. So somehow it like makes me bump every time, but that's ridiculous. That's just like a tradition or what I'm used to. So there's no, so if you do something that, if you, look, and honestly, I'm dwelling on this because I love it. Anytime anybody gets into a detail like this in the chat or in their own head or at home, it means like you're really thinking about the homework and you're trying to do things in a way that actually work for you. And if you feel the freedom to change little details so that the whole bigger picture snaps into place more for you, then you really are thinking like a physicist. Anybody who would have the guts or the flexibility or the desire to make little notational changes so that it works for them really is thinking like a physicist, honestly. So the two of you who are in chat in this conversation right now, like seriously, the reason I'm stopping on it and expanding for everybody is because it's totally worthwhile. So yes, awesome. All right, but what I'm getting here is this. Okay, I'm going to repeat it on the next. Well, I'm going to rewrite this on the next page. But here's the answer. And specifically, here is the answer. This is literally the answer to the line of charge where we were given the density, the linear density of the one-dimensional density of the charge, um, and where some displacement r away from it. We're saying the field direction is always radially away from the line of charge, and the field magnitude is given by this expression. Um, I mean, so let's analyze it for a second or make sense out of it. Or point to line. What's going on? Okay, there's 16 minutes left. Please notice this pattern that's developing here. When it's zero dimensional asymmetry, when the field lines go the same in all dimensions of a three-dimensional space, the law or the wait, one second. Oh, okay, sorry. Just before I go any further, someone in the chat, what is step three for all this? Step three for the like GDP for the larger problem solving method for all of this, for any time you do any of these Gauss's law problems, the equation for step three is definitely is Gauss's law itself, which is this. That if you're doing when you're doing the five-step problem solving method, the step three GDP. Okay, cool, cool, cool. Okay, okay. So that, all right, good question, good question. And thank you for the loop closing. Okay, so what I'm saying to everybody now is when you have zero dimensional asymmetry, a point, or in fact, a sphere, right, or a spherical shell or something, the field lines go out the same in all directions, all dimensions of a three-dimensional space. And so the field is inverse r squared. Remember, we said not coincidentally, like it seems really obscure at first, but what I'm basically saying is if there's no asymmetry in a three-dimensional space, you have an inverse r squared law because the field spreads out in the same rate as the surface area of a sphere gets bigger, right? That's the r squared in the denominator. But now I'm saying go up a level of asymmetry, go from 0 to 1, like go from a point to a line. We now have one-dimensional asymmetry, and the field function that we get is very similar looking. Like it's no longer Q that's causing the field, it's now lambda. Same idea, right? It's not a point of charge, it's a line of charge, lambda, but we've got the charge in the numerator. We've got a constant which is really similar, certainly the same units and all that. It has to be. Granted, the one of them was 1/4, this one's 1/2. Why? Again, well, surface area of a sphere is 4 pi r squared. Surface area of a cylinder is 2 pi r L. Okay, so they differ slightly by the number, but same concept. But now here's the key. The variable itself, the independent variable r, for zero-dimensional asymmetry is r to the -1. I'm saying I'll write this. I mean r to the -2. I mean, in other words, the field here is a function of r to the -2. But here the field, when we go up to one-dimensional asymmetry, the field function goes up by a power of r. It's no longer a function of r to the -2. It's now a function of r to the -1. If you see what I'm saying, you'll see two corollaries to this right away. Number one, the same thing's going to happen for the cylinders. Like I may or may not today have time to actually walk through the rest of the cylinder examples from the homework. But just like the direct chat person was saying, like you notice with the spheres, many of the sphere cases ended up being the same as the point case, a field that was inverse r squared. The cylinders, many of the cylinder cases will be the same as the line case, inverse r, not inverse r squared, inverse r. We went up a level of asymmetry, we'll go up a power of r, is what this pattern seems to suggest. That so coral. Right? So if it's 0 degree asymmetry, we get r to the -2 dependence. If it's 1 degree asymmetry, we get r to the -1 dependence. you'll know you'll know you're really following this pattern or seeing this logic. If then when you get to the final example in the sheet, which I'm not going to go over right now, the final example in the sheet is plates or a plate or a plane, a sheet. That would be an object that would have two-dimensional asymmetry, right? Like a plate of charge is putting charge not only along the x-axis, but also along the y-axis, let's say. The field lines, I'm just going to say this now, that's the big picture. The field lines from a plate will go up away from the plate and down away from the plate. Like they'll all be parallel lines because they'll be symmetric in all axes that are remaining. If you see what I'm saying, like the plate has two-dimensional asymmetry, so the lines will be symmetric in two out of three axes. I'm not saying this well, but the field lines from a plate will have two-dimensional asymmetry. Um, they'll have symmetry in one axis, whatever axis is perpendicular to the plate. And if you're following the logic of this, and if you do the Gauss's law and pick the surface correctly and everything, you'll find that the field function from a plate, it depends on r to the zero, right? Because we went from r to the -2 to r to the -1, and the lines from a plate will go to r to the zero, which means one, right? Anything to the power of zero is one, i.e., the r will totally drop out of the dependence from a plate. The field lines from a plate, as long as we're close enough to the plate, will be the field will be constant. That's a big discovery. And we use those plates to make devices in the lab called the capacitors. Um, but that's just you'll know that you understand this pattern if you can see that that would be true. And that's like a checkpoint on your homework. Like when you do the plate example, you should get in the end that the field is dependent on r to the zero, i.e., not dependent on r at all, a constant. Okay, so that's that. We have 6 minutes left. All right, just to make this as concrete as possible, I'm going to do one more example that is from the homework, like the hard, just kind of like last week. I'm going to jump now to the hard. So there's like four cases of cylinders it then asks you to do, right? Two conducting, two insulating. Conducting, it asks you to go inside and out. Insulating, it asks you to go inside and out. I think you can do all of those right now just based on what we just did with the line. But the hardest one, I'll do this quickly. Like if you have, now I'm going to do this quickly. Like I said, 5 minutes, possibly too quick. They have a cylinder whose radius is capital R, cross-sectional radius is capital R. And the charge is everywhere. Like charge is everywhere. and it's uniformly distributed throughout the body of the cylinder. And we want to know, because it's insulating, right? We want to know what is the field at some point inside the cylinder, somewhere where the displacement from the axis of the cylinder is smaller than the given radius of the whole cylinder. Okay, so I'm going to do this quickly. We want to know the field there at a point inside. I'm telling you right now, the field outside, if you're following the logic of this, the field outside, like the direct chat person said, the field outside must be literally the same as it would be from a line. It'll be 1 over 2 pi epsilon naught lambda over r. The question is, what is it inside? And if it were inside a conductor, it'd be 0. What is it if it's inside an insulator? Well, to cut to the chase, well, the field lines are the same as the field lines from a line. They would spoke out from the center of the cylinder like this. Those are the field lines. I have to choose and draw a Gaussian. Now we have 3 minutes. I'm going to do this. We have to choose and draw a Gaussian cylinder. I mean, a Gaussian surface at the field point. I'm going to draw a cylinder. I'm going to choose and draw a cylinder for the reasons that we just discussed. And I'm going to inspect and verify and say, yeah, all the field lines are going to hit that cylinder all equally. So I'm going to cut straight to the chase and say, okay, here's Gauss's law. I've inspected and verified, so I think the E comes out of the integral. The surface area of a cylinder is 2 pi RL. We already established that. The charge enclosed now, this is the only catch to the whole thing, and then we're done. What's charge enclosed? Well, I look at the density. The density, the density of charge per unit volume is a constant, right? So charge enclosed per volume of a cylinder is pi R squared L, right? Area times length would make volume for a cylinder must equal the total charge times the total volume, right? So you see what I'm saying? So the pi's cancel and the L's cancel. So very quickly, charge enclosed, the amount of charge that I enclose in my inner cylinder must be that. It's just like the argument from last week. I'm not going to, but for a cylinder. So therefore, thus E times 2 pi RL must equal Q over R squared epsilon naught. And this R cancels with that R, and we end up having E equals 1 over 2 pi epsilon naught Q over L R times R squared R hat. In other words, this is the answer, and we're done. This is the answer for the insulating cylinder. And it's 130, but just notice, just like going inside the insulator last week, the field is directly proportional to distance from the center. As you get farther and farther out, the field gets stronger because you're in effect standing on larger and larger tubes, cylinders of charge. That's the answer. And okay, you've been very patient. That's a lot. We'll see you in 2 days. Have a good night.
Thank you, Professor.
Thank you, guys. Have a great day. Yes.